Okay, so today I'm going to talk a little bit about social learning, so learning on a social network, but in particular in the presence of zealots. And zealots we think of here as a particular kind of unreliable agent who really don't learn either from evidence or from each other. Okay. So. Okay. Yeah. Other maps. Okay. Okay. So we can think. I mean, social learning is very common in lots of biological systems. In particular, various kinds of social insects. There's the sort of famous waggle dance of honeybees, but there's also lots of interesting nest hunting behavior of all sorts of other kind of species, particularly ants and so forth. And we can think of it as it's also becoming very, very widely applied in areas like swarm robotics and multi-agent systems. And here we've got a sort of stylized example of a search and rescue application. And we can think of it as being comprised roughly as two processes. There's a form of individual learning. We can see here the little drone going off and actually exploring the environment, getting direct feedback, but also agents learning from each other, sharing information, and in particular, from our point of view, pooling their beliefs. So this can be very effective in terms of actually propagating information very efficiently, increasing learning rates. This kind of pooling can also be effective in terms of actually correcting errors to some extent. But it's also, these kind of sort of positive effects also make it somewhat vulnerable to the case where some of the agents are unreliable, because we can have these kind of incorrect opinions then propagating widely throughout a social network. So here we're going to think particularly about probabilistic agents. So specifically what they are, they're agents whose beliefs are represented by a probability distribution over a set of some mutually exclusive and exhaustive hypotheses. And then we've got these two processes, the pooling and the updating. So pooling, we're going to think about in a model here is a kind of geometric pooling, log linear operators, and we've got a long history in probability theory dating back certainly to the late 1960s, work of people like Lindley, and they're sort of motivated strongly from a sort of Bayesian point of view, but essentially all they are is that for the various probabilities, you simply take the product of them to the power of some weights here. The weights are the relative importance of these particular agents. So mostly in this talk, we're going to be talking about uniform weights, although there are some work in the paper where we look at sort of non-uniform possibilities. So there's also evidential updating, which is Bayesian here. And so the important thing to note about this for the model is that we have this kind of likelihood function, the probability of the evidence given the hypothesis. And from our perspective here, this allows us to have a model of the amount that agents trust or distrust the evidence. So we've got this parameter, which we call a distrust parameter, which is alpha. And basically what it is that given supposing a particular hypothesis is true, then the probability that the evidence would report that is 1 minus alpha, and the probability it would report an incorrect hypothesis is alpha, and that's distributed uniformly across however many other hypotheses you have. So what we know is that the lower the value of, the lower the value of alpha, the larger the effect of evidential updating. So a very low alpha value, and we update supposing given a particular hypothesis, then our prior probability will be increased a large amount to be close to 1. The lower the value of alpha, coming down to alpha 0.5, where evidential updating essentially has no effect. Okay, so what I'm going to try to talk about here now is a particular heuristic for mitigating the effects of unreliable agents. And that's what we're going to call bounded confidence. And bounded confidence is simply the idea that an agent limits pooling its beliefs to those other agents whose beliefs are sufficiently similar to their own. So there's a whole bunch of things about what it means to be sufficiently similar and how you measure that, and I'll talk a little bit more about that in a moment. So zealots here are simply agents that are constantly promoting a fixed probability distribution. Most of the results I'm going to show you here are for two-dimensional case, so two hypotheses. So we can think of them as simply promoting a particular probability value. We're going to think about measuring similarity in terms of statistical distance, which is given here, and it's just the sum of the absolute values of the probability all multiplied by a half. So, and then we can say, so similarity is 1 minus that. And basically we've got a similarity threshold which says that agents will restrict their pooling to those that are similar within that threshold, have a similarity to their own bigger than that threshold, if you like. Okay. So what we've got here is an agent-based model, agent-based simulation that we're going to look at. So this is a sort of flow diagram showing the changes that an individual agent goes through within a particular time step. So they start off with some probability distribution. They identify those neighbors that they have that have similarity greater than the threshold to that. They pool with those neighbors. And then we're in a sort of low evidence scenario where evidence is sparse. So they have only a probability row of receiving evidence and a probability 1 minus row that they don't. If they don't, they just continue with their pooled belief as their new belief. If they do, well, they update on that evidence. And there's a probability of epsilon, a noise probability, an error probability, if you like, that they get the wrong evidence and update, and a probability 1 minus epsilon, they get correct evidence. So here are some trajectories of the kind of behaviors you get here. So the red lines here indicate different kinds of zealots. So we've got zealots which are probability 0.2, which is representing, so if one is the probability, so if this, we're talking about the probability of the true hypothesis here. So these are strongly advocating for the false hypothesis. We've got zealots with probability 0.5 who are sort of systematically undecided, if you like. And then probability 0.8, so zealots advocating weakly for the true hypothesis. And the top line is without any kind of bounded confidence. So agents pool with everybody, and you can see that the presence of zealots are highly disruptive. So not surprisingly, zealots that are strongly promoting the false hypothesis, but even zealots which are on this side here, which are promoting the true hypothesis, but only weakly, they can actually also disrupt convergence to a strong probability in the true hypothesis. So you get, so the bottom row here is with bounded confidence with a threshold of 0.7, and we'll talk about those thresholds in a sec. And you can see, well, it does have a positive effect. It improves performance, although it's much more difficult to improve performance in the case, ironically, where it's promoting for the true hypothesis, but only weakly. So a little bit of just a bit of a sensitivity analysis here about how the thresholds affects things. So here we're going to use Here we're using convergence time, which is probability, which is how long it takes to get to within a 0.95 of the true answer, so a probability of 0.95. And basically you can see that performance depends a lot on getting the correct parameter, and those correct parameters range, they change a lot depending on the difference between the zealots. So I just want to skip through that, so I'll catch to this one. So this one looks at, so these are heat maps plotting the value of the zealot against the threshold, and you can see they're going from very little distrust to high levels of distrust. And you can see the darker regions are regions of good performance. And the more distrust that you have in the evidence, the less effective, the more sensitive it is to the threshold value. So some key takeaways. So in a simple probabilistic agent-based model, this kind of simple bounded confidence model can be effective, but it is sensitive to these threshold parameters, and though those vary for different kinds of evidence, but also somewhat more worryingly, it's actually reduced, the effectiveness is much more reduced by a lack of trust in the evidence. So moving forward, we're going to be looking at some analytical models of this, moving away from agent-based models, and some applications to robotics. Thank you.